Hi, thanks for having me here today. You know, Susan was talking earlier about the fact that if you go to the NANOG website and you look at their little guides for how to put together a good talk, you just follow those and you submit a presentation, you're in. That pretty much explains how I got up here today. So hopefully it's valuable to some of you. Today we're going to talk about extension of multi-service networks, and first we'll get into a bit of overview just about the services and the applications that you want to put on your network to make it a multi-service network, the hardware, the architecture, some of the features, and then we'll get into a brief tangent talking about VoIP peering and VoIP architecture, which is usually a prerequisite for having a multi-service network. It's the sort of interesting application you put on there to do that, and then we'll get into the meat of it, talking about how to extend the reach of your network through partnerships. In the spirit of massive overgeneralization, there's two main modes that your network can run in. You plug a port in and you configure it to talk to any other port that's in this sort of general cloud, and that's what we call the internet. And then you have these other types of ports that you specifically configure to talk to other ports, and they can't talk to any other ports. That's kind of like an IPVPN. In addition to all the obvious applications that are internet related that run in your network, some of the other ones that will run on your multi-service network will be a various suite of voice over IP applications, such as toll bypass, which is connecting up your PBXs to talk to each other with IP and not using a carrier, not having to pay for that. And then your toll services like long distance and also local service. And they might have some video services as well, point-to-point video or multi-point video conferencing, and up to and including managed video conferencing services. The framework might look something like this. Capacity running on the very bottom, networking services in the center, your services running on top. You'll have your optical transport network, which probably everyone is running over. And then your core will probably be MPLS based with a variety of different protocols supported for the edge transport, be that SONET, Ethernet, Wi-Fi, frame relay, wavelength services, what have you. Then you could have your two different modes of service, your internet and your IPVPN, and then you layer your services on top of that so that each of your different services that you create has the ability to be delivered over either your internet service or your IPVPN service. Structurally, what this might look like is you might create multiple overlay networks using MPLS. The red lines up here represent physical connections. So your first overlay network, which might be your IPVPN network, has two physical connections into a set of core routers. Your another overlay network might be your internet backbone. It also has a set of physical connections into your core. But then the logical connections between them are built with MPLS tunnels, directly meshed between all the other edge devices in that cloud. And so you have this sort of an architecture, and you can do this with as many overlays as you want until you run out of CapEx for all the edge devices. The key enabling feature behind this is MPLS, at least for Global Crossing it is. It's not necessarily the only capability or feature that you can use to implement that. Also, QoS is a key feature in your core. We use the differentiated services model with three classes of service in the core, BE, AF, and EF. For now, internet is always mapped into best effort, although in the future we'll support being able to have the customer set or purchase varying levels and classes of service in order to access on-net applications such as voice and video. VoIP today is always mapped into EF. It's also explicitly routed across the core. And then IPVPN customers have full diff-cert capabilities, and they can select any of the three classes that they want to put their packets into. Another very important feature to consider in your multi-service core is fast IDP convergence. And reroutes should occur reasonably fast. And please note that this doesn't necessarily imply the use of the MPLS fast reroute capability. We don't need to have 50 millisecond reroute just because they thought that was a good number to use for SONET. 2 seconds or less is a pretty common target for inside a continent. Our network runs a little less than a second in most cases for intracontinental, and 2 seconds or less for intercontinental. And the basic philosophy here behind the timeout is really related not to devices or applications automatically resetting, but more what the end user is willing to tolerate. It's somewhere between 2 and 6 seconds where you get tired of saying hello, 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 and then you hang up. This is where we take a little tangent to talk about VoIP architecture and what this is comprised of. Global Crossing has one of the largest VoIP deployments in the world. We use Sonos equipment. GSX is the gateway device. It basically has a TDM on one side that connects out to other TDM switches out there in the network through vendors and customers. PSX is used for the brains of this network, brain dead voice routing, that is. The GSXs are actually pretty stupid. They don't have any routing tables in them at all. They have to ask the PSX, which is a database that runs on a Sun system essentially, what all the routes are. So whenever a call comes in, they have to ask the PSX where to send it. They send it over to the terminating GSX. That GSX has to ask the PSX, is this a customer of mine? Why am I being given this? To figure out how to route it out, which trunk group is configured on it. And then the voice network also has this SS7 signaling that is very important to make that all work. And the SGX plugs into the SS7 network and is used to communicate from a signaling perspective with the SS7 network, and thereby establish calls to the TDM network, the PSTN. Now, this piece of it in green on the left side of the slide, this is all pretty much the commercial long-distance voice side of the house. When we talk about taking VoIP out to customers to carry it across our multi-service network so our customers can use these services, there's a couple other pieces of equipment that become very important. One of those is the System Border Controller, the SBC. We use a company called Acme Packet for this role. There's probably half a dozen major players in this market out there right now. The role of the Session Border Controller is twofold. One, it provides double NAT capability so that your RTP sessions that go between your GSXs or your other gateway devices and your customers or your vendors out on the IP network, it'll do a double NAT on those RTP sessions. Another very important piece, though, is that SIP and also H323 have the unfortunate feature that the source destination information is actually included inside the header. So the Session Border Controller plays the role of a back-to-back user agent for the signaling, actually terminating the incoming signal, turning it into an abstract language for where it needs to go, doing a lookup with the PSX, and then initiating a new signaling session, a SIP session, inside the VoIP network. Because a lot of these networks are running compression, particularly the networks that service end users like the Vonages of the world, they want G729 capability turned on by default, since all the phones are set to use that. They don't want to convert it back to G711 since that's very costly. So they'd like us to do it, so we also have to deploy a compression chamber for calls that require it to take that and convert it from G729, which is a compressed call that takes around 32 kilobits per second, and re-encode that as G711 with silent suppression, which is what our 4 uses. In the voice world, and this has probably been touched on in a number of NANOGs past, there's no such thing as a voice peer. Kind of like on a Cisco or a Juniper, you can configure a peer, but just because the technical term is peer doesn't mean that the thing on the other side of that is actually a peer. It could be a customer, it could be a transit provider, and it's pretty much the same in the voice world. except that there are no peers. There is no one that you exchange traffic with freely. And that's because the model for the traffic is pretty simple. Either you're receiving a call and then you're being signaled to set something up and deliver a call, or you have to deliver a call and you're sending a signal out saying, I need some help delivering this. So you either have customers or you have peers. Or excuse me, you either have customers or you have vendors. So in terms of moving to VoIP, there's the first people that wanted to move to VoIP were international carriers, people that didn't want to pay for long-haul connections into the United States in order to accept your calls and deliver them internationally. They wanted to use the internet for that and be able to do that at much reduced rates. So those are the first people that were really clamoring for us to give them their minutes via IP instead of TDM. We've even had some interest from RBox. They don't want to be left behind in the VoIP world, but they also they don't want to take them for free either or do vastly reduced rates. They want to do it within the confines of some existing tariff so they can still get paid a reasonable amount for that. And then also because you want to give it to an RBoc with an IP packet doesn't make it enhanced. And this enhanced terminology is pretty important because enhanced means that you wouldn't have to pay them in order to terminate it. You wouldn't have to pay the tariff rate on that. The important thing here is that if the call is being delivered to an end user who has an IP telephone, then that could be enhanced and could be considered an information service, and you would not have to pay toll charges on that. But if you're giving it to someone who is going to convert it back into TDM, then that call is not enhanced and doesn't qualify. This is what I think the future of this voice network looks like. If we go back 2 slides real quick, we see that we have enterprise customers that are sending and receiving calls from us, and this is great because we're probably getting paid to receive the call, and we're delivering it to the enterprise customer at no charge. We're receiving calls from the enterprise customer, and we're charging them for that. We're receiving calls from the carrier voice customer, and we're charging them for that. And then we're paying hopefully a slightly less amount to terminate it to a carrier voice vendor. And this model works great. The SBC actually hides all the information about where calls are coming from the people that are receiving it and vice versa, so we can ensure that we stay in the revenue stream somewhere. In the future, though, I don't think we'll be so fortunate. This is the great thing about the internet, is we can't keep peer-to-peer from occurring. There will be public domain call managers that allow you to get into communities of interest to complete your calls over the internet. There's already plenty of these out there, Skype being a prime example. There's also capabilities being built into commonly available IP PBXs such as Asterisk, and this will be announced at VON, which is also this week. Some new work that's being done to do some auto discovery so that your PBX can automatically figure out where other prefixes and other destinations might be, allowing you to completely avoid your long distance company altogether to complete your call. So if you want to convince your company that they should let you run all these fancy applications on your network, you might encounter some internal resistance. This is pretty common. There's a number of internal challenges that you'll face in terms of getting this accomplished. A few of those are technical. The first thing you need to do is you need to demonstrate to your management, to the naysayers, especially to the voice TDM people, that QoS does actually work. So you'll need to spend some money on some lab equipment that will enable you to set up a mock network, to actually run some tests and demonstrate that QoS is going to perform as you indicate. You'll also need to demonstrate a reasonable implementation cost. And this can be a little difficult if you have some older equipment in your network. Not necessarily cheap equipment, but older equipment. For example, the Revision A OC48 card that runs on the Cisco GSR does have a glitch in the hardware that didn't really make sense in terms of a QoS implementation. Some of the older FPCs on the Junipers, not to pick on Cisco too much, also have some issues in certain configurations. So if you have to replace this equipment, you could be talking tens of millions of dollars depending on the size of your network. From an operational perspective, you have to convince these people that your network's up to the task. And the best way to do that is to show them that it can actually run at 5 nines of availability or better. On our network, the IPVPN overlay runs at in excess of 5 nines. The VoIP network overlay runs at almost 6 nines. The internet network runs at not quite 5 nines, largely due to the impact of DOS attacks and other security issues that arise as a result of it being on the internet. Another cool thing you can do is if you can convince your internal, your information technology, your internal support teams, what have you, to deploy IP telephony internally as a cost savings measure, you can then also demonstrate the quality of voice over IP to those that are a little skeptical about its performance. There's nothing like calling the senior vice president of voice operations up on an IP telephone and having him realize that the quality is superior to the PSTN network that he's been accustomed to. You might have some organizational challenges to overcome as well. You have to bring your voice and data organizations closer together. Even inside your information technology group, you might have one organization that is in charge of the PBXs and another organization that's in charge of data. And you might have trouble deploying IP telephony because the voice division is worried about losing their jobs and whatnot. Also, for the people that are running your voice network, that's also going to be a concern for them. Job security is going to be a problem that's going to present itself politically when you're trying to make this deployment. And so if you can build a career path for these folks so that they get some IP training, that presents some opportunities for them to grow and to not be cut out of the loop, and you take that problem away. If you're a peering coordinator and you want to extend your network to create some partnerships, imagine if you just went out and found a peer and turned a few of these things on: interprovider MPLS to do IPVPNs, interprovider QoS, and inter-AS MPLS. Your peer decides that he wants to start sending some reservations to you with RSVP, and reserves some nice big 1 gigabit per second paths across for his Ethernet connection for some customer of his, and nicely consumes a whole chunk of your capacity on your network and throws all of your modeling off. Or another thing you could do is he could take those IP precedence bits that are coming in that would be sent across your network and that his customers would normally be sending, and he could say, oh, well, I'm going to differentiate myself in the marketplace by guaranteeing that my customers always have the best performance on your network than all of your customers. And so he's going to reset those IP precedence bits so they don't get set properly. Some of the possibilities here make it pretty clear that you're creating much more than an ordinary peering session, and you have much more than just an ordinary peering agreement. You probably are thinking, well, gee, I should be able to charge this guy for the amount of bandwidth he's reserving on my network, and there should be some parameters about the class of service values, or maybe even a rate structure around how much traffic he sends me in each one of these classes. So that raises a whole bunch of questions. Is this peer a partner of mine? And on ATM networks, when we didn't have any peering, we had these network-to-network interfaces, and we used them to extend the reach of our network. We clearly identified these NNIs in our provisioning systems. We established them following a discussion about an actual partnership. We didn't just casually enable NNIs with everyone else to create this global ATM internet. We actually did it for very specific reasons. So there was a commercial agreement that came about, and if we apply that to our partnerships and our extension of our multi-service networks, we're looking at much the same kind of thing. We're looking at a commercial agreement that looks very similar to what we had for ATM NNIs in the ATM world. And if you think about it, a lot of your peers that you have today, they're probably in direct competition with you. They don't really have any interest in lining all their features and capabilities up with yours and a number of other things that would be appropriate for partners. They may not even want to enhance the performance of the applications that they sell across their network boundaries out of concern that some of the applications that you sell might be sold to their customers and might cut them out of their value add profits and their additional margin that they're looking for. So you're going to go to someone that you want to have a much stronger commercial arrangement with, and you're going to start working on an agreement. And here are some of the aspects that you want to look at for that. The first thing that comes up is branding. In other words, who goes to the customer, and what's the name that's presented to the customer, and how is that all presented? Is that done under my company? Do you go to one of your potential customers and tell them that you're selling a global crossing service? Or when you go there, do you make it look like you're the sole provider and you're managing everything? And then you include in the agreement who's going to be providing all the frontline support for that end user, what the variety of services are that can be sold, the service features that are supported, cost structure, who's the customer going to get the bill from, and then some of the things that make the service work better. How are we going to work knock-to-knock communications? What's that going to look like? Does OSS information need to be exchanged? Is the arrangement going to be bilateral? In other words, if you can go to one of your customers and sell them services on my network, can I go to some of my customers and sell them services on your network? And then also, what is the architecture? And more on that last bullet about the architecture, there's a couple different ways you can do it. The common way that we've done with most folks so far that we've built connections with is an inter-provider MPLS Type A connection, which is really nothing more than a packet over SONET OC3 or OC12, which is set with firm relay encapsulation. And then what you can do is you can take on each one of these PVCs that you configure, you can manually provision those into a VPN, and it basically resembles a lot like a uni in the ATM world. It's okay, it does the job. It inserts a layer 3 hop in the customer VPN, which they can see so they can tell they're going across an NNI. The provisioning is manual, so somebody has to go in and configure the customer connection specifically. Also, redundancy has to be designed and configured on a per VPN basis. So if I have 2 NNIs or 2 inter-provider connections with another carrier, I have to go and configure 2 PVCs in that customer VPN, and then I have to do specific dynamic routing across those connections just for that one VPN. There's also no visibility. If the customer port on the remote network goes down, I may have no clue that that's gone down unless the customer calls me and lets me know, or it happens to be a managed service. A much better way to do this is to use inter-provider MPLS Type C with a partner. There's no layer 3 hops. It's totally seamless thanks to MPLS. Provisioning can be somewhat automated in that the remote network can configure customer ports on their network, and the information is automatically exchanged between our route reflectors. Also, similarly, redundancy is enabled across those VPNs automatically due to the route exchange between the route reflectors. So if one NNI goes down, all of the VPNs are automatically rerouted to another NNI. There's also some enhancements that can be made on the OSS side, which can vastly improve the quality of the product that you're selling through these partner networks, and that is the exchange of network alarms between your event management systems, so that if you'd like to proactively notify the customer, you're not going to have that information available to them. And also, exchange of relevant network statistics is very important for your billing and your portal system, so that when your customer is looking at your web portal and wants to look at the utilization of all his ports, he needs to be able to see all of his ports included in there, not just ports that happen to be on your network. And then this last bullet is one that tends to get overlooked an awful lot, and that is that your product features and your capabilities must be aligned. And this is where it becomes very clear that this is a partner and not something to be casually enabled with someone. If we go into more detail on that, the biggest problem here is going to be inter-provider QoS. There's a number of product issues that come out of this. It's pretty trivial to just enable QoS on a link to a partner. You can set up mappings as if they were any other customer. You can put packets into the queues, and your partner can do the same thing on their end. But what you tell your customer in terms of what's taking place might not necessarily be consistent. For example, if one provider, like Global Crossing, for example, supports a feature like maintaining the transparency of the original IP precedence bit, in other words, the IP precedence bit on your packet that comes into us is going to be the same value that is there when the packet leaves our network. Well, not every network out there has that capability. Some of them have to rewrite that precedence bit in order to match up the class of service in their own network. And so that's going to break our feature. We won't have that feature available globally with peers that don't support that same capability. Another clash that often comes up is some providers decide to deploy differing numbers of classes of service. And I'm not necessarily saying that 3 is better than 8 or 8 is better than 3. There's not necessarily a better answer here, but the fact that there is a difference between providers is what causes the problem. And so usually it's the one with the larger number of classes that when they have to enable services across a partner network has problems with being able to maintain all of those classes and maintain the sort of performance characteristics across any port. So being a partner means more than just doing inter-provider MPLS, having inter-provider QoS, OSS, NOC communications. You have to align your products and services that you want to sell with your partners. And that is something that should take place between your marketing and your product management organizations. To get aligned on that, partners should be carefully selected, et cetera. There's one last piece of this before I close today. What we're seeing out there is in addition to some backbones that have been implementing MPLS for some time now, we're also starting to see local, regional, metro carriers implement MPLS as well, which is a bit surprising to me at first, but it is happening. And so if you think about it, today, as a backbone provider, we have to purchase most of our services from some sort of local carrier. And if they're deploying IPVPNs and they're deploying MPLS infrastructure in their metro areas, what if we use this same technology to extend our network across vast regions? What if we also replace our existing entrance facilities, which are TDM-based, with an MPLS inter-provider connection? We could use it for extending IPVPNs natively through local areas. We could use it for selling internet access pipes, for delivering L2 VPNs such as Ethernet, and also for selling VoIP over that variety of connections. And it would be a cleaner and much more efficient use of capacity across the local boundaries between the IXC and the LEC. There is some work taking place right now. British Telecom in the United Kingdom is quite interested in this. They have there's also an organization called the NICC, which is specific to the United Kingdom, and the whole British Telecom 21st Century Network revolves around a lot of this, and we're seeing some very good support there. Not too much in the United States yet, though. That concludes my talk. Thanks very much. Any questions?
Hi, Dave. I was going to ask you if you found any particularly good resources either on the web for voice over IP introduction, the technology, all that kind of stuff, or if there are any books that are like the books you need to get.
I'm sure there probably is. I had to learn it all the hard way, which is market requirements documents and trying to make the products work.
Do all of these interworking with other providers work over private exchanges, or any of them work over exchange carriers such as Equinix?
In theory, they could run over a public exchange. I don't see why they couldn't, since basically a pairing session is the key enabler there between the route reflectors. But none of our connections are over public exchange points, although we do have some that are private connections inside Equinix facilities.